Hello, I'm David. That'll do. I'm the coordinator of the Maths Learning Centre. It's semester 2, 2017, and this is a Maths 1A revision seminar. I did one yesterday, which covered various things, and now I've got a couple more things on the list. And people have asked about a few integral sort of things, and so I might talk about those. So I'm not going to do all of integration, and just some specific ones. Let's do some specific integration stuff. So I was specifically asked to talk about integration by parts and trig substitution. And so I'll have a chat about them. And if anyone has some other questions about integration stuff along the way, feel free to ask, and I'll talk about them too. Okay. Integration by parts is a technique for integration, obviously, that is the sort of the third one on my list when I think of what things I might try for integration. So when I'm trying to integrate something, the first thing on my list is to just check to see if something I already know how to do without having to do anything special. Actually, it's the fourth one on my list. Sorry about that. And then the next thing I would try is to maybe rewrite it somehow, to maybe expand some brackets or factorize or use a trig identity. And then the third thing I would try is to check to see if I can do it with substitution. I wouldn't actually sit down and attempt to do any working for this. I'd just have a look at it to see if it seemed reasonable that I could do it these ways. And then the next thing on the list is integration by parts. So my first piece of advice with integration is that first check if there's not an easier way to do it. I mean, obviously, if someone says to you, you must do this by integration by parts or I won't give you the marks, then you do it by integration by parts. But if they just say do an integral, don't automatically go to integration by parts as your first port of call. These ones are usually easier. So you try to think about them first. Right. My big advice for all integration, actually, is to see if there's an easier way to do it. Right. So the way that integration by parts works is it's specifically designed for things that sort of aren't already in these and are two functions multiplied together. And this bit here is the key. Two functions multiplied together. They're the two parts that you're referring to. And just like substitution, it doesn't actually do the whole integral for you. Once you've done your integration by parts, you've just turned it into another integral that you have to know how to do afterwards. So when you do substitution and when you do integration by parts, once you've done that bit, then there's another integral to do afterwards. So So it turns your integral into another one that you have to do afterwards. That's an important thing to consider, and that's because you have to know how to do that integral after you've done the integration by parts. If when you do the integration by parts you get another integral that you still don't know how to do, then you've wasted everybody's time. Okay, so they're just some two thoughts about it. And it goes like this. Because it's designed for things that are multiplied together, it sort of belongs with the product rule for differentiation. So when you do differentiation and you have two things multiplied together, there's a rule for that. It's called the product rule. And integration by parts is designed for things that are multiplied together. So in a way, it's the product rule for integration. But it's not as nice. So there are two ways to try and remember it. One is to remember it, and the other one is to derive it from the product rule. And I'll show you both. So way number one is to derive it from the product rule. And that it looks like it's one word, I'm sorry. So I could derive it from the product rule, which means this. I know that if I have two functions multiplied together and I differentiate them, then I get the first one differentiated and the second one not. And also the first one not differentiated and the second one yes. That's the product rule. And then what I do is I integrate everything. And because integration has the property that it distributes over plus, I can just do each part separately. And the integral of a derivative is the first thing you thought of. And so what that means is that if I have either one of these two integrals that I want to figure out, then I can figure out the other one instead and just use this formula to figure it out. So I could put either one of these two over there. So I'm just going to write this backwards. Like that. And so I get a choice. I can either put this over there, like remove it from this side, and in which case it would have to appear over there with a minus, or I can remove this one. Like that. I could just as easily have moved the other one, and it would have been fg dashed and f dash g. I think your lecturer uses u and v, but you can use whatever letters you desire. Okay, so that's purist. It's based entirely on my understanding of differentiation. But a worthy point is that I could have moved either one of those, so it doesn't matter which one of them has the dash, and as long as the other one has the dash over here. So number two is to not derive it, but just remember that, which doesn't really count as a technique for remembering, but you just remember that. And I will show you how I write it. It needs to be seen live to show you how I learned to remember this. When I was in first year, in every time I had to do this in an exam, I did this, because I could not, for the life of me, remember it, so I had to derive it. But then I learned how to remember it. So you can remember the structure. So this is how I remember it now. I know that there's an f times g in all three of them. And I know that this one has an integral, because that's what I'm trying to figure out. And this one has an integral, because it turns it into a new integral. I know this is a minus just because I remember that. And then finally, I know that one of them has a dash over here and the other one has a dash over here. That sounds strange. Well, hopefully it doesn't. I remember all sorts of things in the wrong order. Like my trig identities, I tend to fill them out from the other ones. So if you would like to try and remember it to begin with, just be able to remember it straight up, then find a way of noticing the structure of it. All three of them have two things multiplied together. One of them has is a derivative over this side, the other one's a derivative over this side. And there's two integrals, one on each side. That's sort of how I remember it. If all else fails, you can always derive it from the product rule. Okay. And if I was going to use integration by parts, then I need to decide what is going to have the dash. So let me do an example or two. This is the classic example that everyone always does. X e to the something x. Okay. So if I wanted to integrate that, one of those is, one of them is f and the other one's g, and I have to decide which of them has the dash. So I'm going to do this for my own purposes. I'm just going to make some space. I'm going to need to know what f and g and f dashed and g dashed are. And in my head, derivatives are down and integrals are up, so that's why I've written it the way it is. Okay? And I'll just figure out what they are in a second. Okay. And I know that this is going to work out to that, because that's how integration by parts works. It turns fg, but one of them has a dash, into fg minus the integral of fg, but the other one has a dash over the other side. So all I need to decide at this stage is whether to go f dash g here or fg dashed here. So, right. So here's how I make the decision. My decision is that I have two rules for telling. So I know that if something is f dashed over here, then I'm going to have to integrate it to figure out what the f without the dash is. So I have to know how to integrate it. If I don't know how to integrate it, then I can't choose it to be the thing I integrate. So the one that has the dash, I have to know how to integrate it. And I know how to integrate x, and I know how to integrate e to the 3x, so that particular rule doesn't help me make my decision, sadly. Okay? So the next thing I might do is then I need to decide, well, since I can integrate both, I get to choose which one. And the thing that I differentiate, I would like to become easier, make everything easier afterwards. So if I differentiate e to the 3x, it'll be 3e to the 3x, which is just the same as it was before. So that's not really any better than it was. And if I differentiate x, it becomes 1, which is much better. I can deal with 1. So I'm going to make x the thing that I differentiate. So I'm going to put the dash here. Okay, so I've got x and e to the 3x. That's what I've decided. There we go. I've now made my decision. Now that I've made my decision, I can just track everything through. F is x, so f dashed is 1. G dashed is e to the 3x. So when I integrate that, I'll get e to the 3x, but I'll have to divide by that 3 because I'm integrating. If I was differentiating, I would have to multiply by that 3. And now I can fill in the details down here. F is x, g is 1/3 of e to the 3x. F dashed is 1, g is 1/3 e to the 3x. Okay, and now look, as I said, there's another integral for me to do. But I know how to do this integral. It's just e to the 3x with a constant, so I can do that. So the 1/3 is multiplied on, so it will still be there. The integral of e to the 3x is e to the 3x, but I have to divide by 3. And I have just enough room to fit the entire thing on the screen. Like that. So let me just run through what happened there. As integration by parts does, it turned my original integral into a bit and then another integral that I still had to do afterwards. I had to decide which of these was the dash, which one of them I would come down and which one of them would go up. So I could have chosen to have x and e to the x or this way round. I chose this way round because it made this one practically disappear. It became a 1, and when you times by 1, there's nothing changes. So that's my decision. Let me just do another one. Okay, so that's classic integration by parts. There are all sorts of examples that people use. And it's often polynomial like x, and then next to it something that's less pretty like sine or e to the x. That's often how it's done. There are two special tricks. I hate to say the word trick because it makes it sound like magic, but there are two special techniques that allow you to do integration by parts even when it doesn't seem like it's something that you might be able to do. So one of the classics is this. The integral of arctan, for example. Now let me just make sure that I'm doing my job properly. I should go back and see if I have ways of dealing with this. So let's see. Can I just do it? No, I don't know what the integral of arctan is. I know what the derivative of arctan is. It's 1 over 1 plus x squared. I can do that, but I can't do the integral. Rewrite it. So can I rewrite that in any particular way? Well, if it was just tan, I could rewrite it as sine over cos. But arctan doesn't work that way. It's not like arctan is arcsine over arccos. That's not how the arc works, so I can't do that. Substitution, what the frell am I going to substitute? Because for substitution I'd need a function inside another function, which I totally don't have. All I have is arctan. So integration by parts is the thing I should be using. But it was worth checking first, just in case there was an easier way. Except it doesn't look like integration by parts is going to help, because integration by parts is designed for two things that are multiplied together. So how am I going to deal with that? Well, I can always do this. Now it's two things multiplied together. Nice. I really should have left space to do my F's and my G's, so I apologise. So you'll notice something. Whenever I do my working, I rewrite the thing that I was trying to do. So if you were in an exam, this would be written on the page already. So you wouldn't have to rewrite that here. I would start by doing this. So just pointing it out. It's also good practice to start with the thing that you're aiming for. And this is supposed to be F and G, so that this works out to be like that. I just have to decide what has the dash. But here's where the first thing I said before is, if this one had the dash here, I'd have to integrate the arctan to figure out what the g is, and I don't know how to integrate the arctan. That's the whole point. I don't know how. So it has to be this one. Like that. So you could look here or you could look here. If I wrote the arctan down here, I'd have to integrate it, and I don't know how, so I'm going to write it up here, which puts the 1 down there. So the integral of 1 is x, and the derivative of arctan is 1 over 1 plus x squared. And so therefore this, just enough room, f is x, g is arctan, minus the integral of f, which is x, and g dashed is 1 over 1 plus x squared. And now I have a new integral that I need to do. Okay, so if you really want to commit to this properly, you could actually rewrite that and figure out what that integral is. So, in a way, from this point forward, I'm going to ignore everything that I just did and just do this integral. Cross it out too. Are my hands big enough to do that? Yes. I'm just going to do that integral there. So with that integral there, I'm first going to stare at it and say, do I know how to do that straight off? No. Okay. Can I rewrite it? If it was 1 plus x and the x was on the bottom, 1 plus x squared and the x was on the bottom, I could just divide them separately by x, and then that would be 2 separate pieces that I know how to integrate. But because the plus is trapped underneath that fraction, and fractions don't interact with plus on the bottom, I don't have a hope with that, so that's not helpful. So substitution is the next on the list. So for substitution, I'd pick something to be u and hope that the derivative of u was there somewhere. And usually you pick the most annoying bit, and I've just talked about how the bottom of the fraction was really annoying. So if u was 1 plus x squared, the derivative would be 2x. Well, that's nearly the same as the top. That sounds like a good plan. And du on dx would be 2x. And so du would be 2x dx. But I don't have a 2x, so I'll just do this. Okay, so now this is here and comes out to half of du, and this is here and comes out to u. So I can do that. Let's just figure out what that other bit is. So the integral of x on 1 plus x squared dx is the integral of the x dx was a half of du, and this was u, and I know what the integral of 1 over u is. That would be ln u. So I've got a half of ln u, but u was 1 plus x squared. Oh, look, 1 plus x squared is always positive anyway, so I don't have to worry about the absolute values. All right, so I'm nearly done. Where was I up to? So I had so far that the integral of arctan x dx was x arctan x minus the integral of x over 1 plus x squared dx. That's what I had, and I just figured out that this thing was a half of ln 1 plus x squared. Crap, sorry. Right. Done. So you'll notice there, that I had to do integration by parts and then a substitution. Now, there's no particular reason that I have to know in advance that I have to do a substitution. The integration by parts was the only option I had to attempt to integrate that. And then when I looked at this one, substitution was the first thing I thought of that helped. Yep?
Just a question, would I be able to rewrite it just before we started doing the substitution? Rewrite it as, what was the original one? Right at the top. Yeah, there. And rewrite it as 1 over 1 plus x2, just the way it is there, and then just integrate each one of them separately. The 1 over 1 plus x2 is ln of 1 plus x squared, and then do the integral of the x as well, and then give me the same, because I might make mistakes.
The whole point of integration by parts is that you can't just integrate two things that are multiplied together separately. And so if you see two things multiplied together separately, you can't just integrate them separately, because integration by parts is more complicated than that. And plus also the integral of just 1 over 1 plus x squared is not ln 1 plus x squared, it's arctan. Because of the chain rule, you have to have the 2x there if you're going to be able to do your ln. So unfortunately, our only choice is to use substitution for this, sadly. So you could see this question would have an exam writer very excited, because it doesn't just use integration by parts, it also uses substitution. And they're great lovers of exam questions that involve two things, because they get to assess two things at once. And they've only got 3 hours, right? Okay. So that's special trick number 1, which I better write down. Actually, I'll just summarize them at the end. So first we had, I need to choose the thing that gets differentiated, the thing that is eventually has a produces a dash afterwards. That has to get simpler. This one I have 2 techniques. One was, well, if it doesn't look like it's a multiplication, just do 1 times and see what happens. And also, you can only integrate things that you know how to integrate. So if you're going to have to make a choice, differentiate the thing that you don't know how to integrate. And the third thing with integration by parts is that you might have to do it more than once. In fact, that's not even the last thing. You might have to do it more than once, and you may have to pay very close attention to see if the thing that you produce afterwards is the same as the thing that you started with. I call this going round in circles, or possibly going forward to go back. It's a little bit like in Willy Wonka and the Chocolate Factory. Yep? I have no idea if they're going to ask you true or false questions or fill in the blank questions. They might, but I didn't write the exam. I haven't even seen the exam. I only get to find out about the exam when people come to me afterwards and say, David, this is what the exam was like. I haven't even seen that. Unless people, they either mention it in passing, and I can't remember any. No one came after last semester's exam and said, this question was absolutely awful, which is what they usually come and tell me. But also, no one sat down with last year's exam and said to me, David, this is last year's exam, these are the things I'm not sure. So I just can't tell you. Your only way of knowing what your exam writers are likely to do is to look at the past exams yourself. There's nothing stopping them doing a true or false. They might do a true or false and say, integration by parts will help you perform this integral, true or false. And you could say, if you saw an arctan, you could say, yes, yes it will. Because now you know, you've just seen it. But that's all I can, I can't give you anything else on that. For other things, like for subspaces, it's common for them to ask yes or no, true or false questions. They'll say, you know, can this be a basis for R3? And you say, no, because it's only got 2 vectors, that sort of thing. Yes? Yes, you could have called, What letter you call them isn't important. I could have called this one G and this one F. No. The important thing is which one has the dash and which one doesn't. What letter you call them is completely irrelevant. On some days I use U and V. I wouldn't normally write GF because they're in the wrong order alphabetically, and that just, you know, I don't feel comfortable putting things in the wrong order alphabetically, but that's not really a maths thing. That's more of a just David's analness. So okay, so there was one thing you had to do.
Oh yeah, just wanted to make a comment on his true or false thing. There is a lot of true or false, not a lot, but there are. The past exams there have been true or false questions. I'm just going to let it know.
So in past exams there have been true or false. As I said, they're more common in algebra than they are in calculus, but not impossible in calculus. Sorry? Really? And you had to give like a little reason as to why?
So you have to calculate it. It's just like as if they say calculate and calculate, because you need to show that it's true.
Yeah. But true or false ones in a maths exam are usually the sort of thing that you can reason out rather than calculating.
Did they ask for counterexample?
Yeah, like is this integral greater than 4? And you can go, well, no, because this number is always less than 2, and so that's why. Okay, so I did have one more example to do, which was of the going round in circles. Give me a second. I'm just trying to decide how crap I want it to be. Let's go all out. E to the 2x sine of 3x. Okay, so let's just run through it and let's just, can I just do it? Well, if it was just e to the 2x, then sure, that'd be fine. If it was just e to the sine 3x, then yes, I could do that too. But at the moment, no, because they're multiplied together. The multiplying together is hinting at me that integration by parts would be a good idea, but just give me a second. Could I rewrite it? Not without using complex numbers. If that was sine 3x, then I could probably rewrite it in terms of e to the power of stuff, and that would be the easiest way to do it. Okay. Substitution. Yeah, nothing's going to get rid of that e to the 2x. So yes, integration by parts is the good one. All right. So let's see. Whoa, no. So they're just as easy to integrate or differentiate as each other. And neither of them is going to get simpler, right? The e to the 2x is still going to have an e to the 2x afterwards. The sine 3x is just going to be a cos afterwards. So really there's not all that much I can do, so I should be able to just pick them whichever way I want. So let's just do this one. No, I won't do that. I'm going to do it this way. Do you know why? Because when I differentiate sine, I get a plus instead of a minus. If I integrated sine, then it would have become a minus cos, and I can bet my bottom dollar I would lose that minus along the way, because I'm always going to lose a minus sign when I do my working, so I'll try and avoid it as much as I can. Okay. So when I integrate e to the 2x, I get a half of e to the 2x. When I differentiate sine, I get cos, but I'll have to multiply by the 3. Be very careful. It is very, very common for people to integrate when they was plan to differentiate, but then integrate anyway, or vice versa. So just pay close attention to what you're doing. Yep. So this is f, g, like that. Okay. So what have we got? We've got f is a half of e to the 2x, and g is sine 3x. And f is a half of e to the 2x, and g dashed is 3 cos 3x. Now what have we got? 3 halves. Right. Well, we've got a new integral. Let's see if we can figure out how to do it. Can't rewrite it. Crap, it's another integration by parts. I'll just have to do another integration by parts. So, here we go. All right, so the integral into e to the 2x cos 3x dx. And that's going to be like I've left a gap, just be aware. Now I've already used f and g, and that's just going to confuse the person who's reading it. So I might h and k, hey? Okay, so let's see, h dashed, k. I need to put primes in here? Yeah, I'll figure that out in a second.
Oh, yeah.
I'll get there. Okay. All right. Well, I've got the same dilemma I had last time. If I integrate, I can integrate or differentiate either of them. But I do have to be a bit careful, because this cos 3x here, if I integrate that one, I'll just go back to where I started. Like that 3 cos 3x, if I integrate that one, I'll get like a third of sine 3x, which will cancel out that 3. And everything will just go back to where I came from, and I'll end up with everything will cancel out. So I have to go forwards. Yep. I know, but it'll cancel out the wrong way. I need to go forwards to go back instead of going back to go back. So look at this. In order to get from where I am to here, I made the choice to differentiate, to integrate the one that had an e. So I'm going to make the same choice the second time. I'm not going to do the opposite choice that I made last time. I'm going to make the same choice that I made last time. So this time I had the dash here and here. And I will do the same. Very important to make the same choice you made last time. So the first time I integrated the one with the e, the second time I'll integrate the one with the e again. So when I integrate that one, the 3 on 2 will still be there, and then I'll go e to the 2x and I'll divide by the 2. So if I just give myself a little more space, I can say that that's 3/4 of e to the 2x. And that was cos 3x. And that becomes minus, damn it, I can't avoid the minus. I'll just have to be really careful when I get there. So let's see what happens. I get h is 3/4 e to the 2x. K is cos 3x. H is 3/4 e to the 2x. And k is minus 3 sine 3x. So that minus could go with that to make a plus, and then I'll have like 9/4. All right, so let's just write down where I'm up to. So the integral of e to the 2x sine 3x dx is half of e to the 2x sine 3x minus this answer. Right, and so I have another one. I could, if I desired, do more integration by parts, but it would just keep flipping, flopping back between the sine and the cos, and this number would just keep getting bigger and bigger. But I have got something. This thing is almost the same as what I started with, except for the number's wrong. So, if I just remove this from this side, which would put it over here, I'd end up over this side damn it. Well, I had one of them before, and I'm going to add 9/4 of it onto it. So I have 1 9/4 of this integral. Like that. Yes. So what's 1 9/4? Well, 9/4 would be 2 1/4. So we've got 3 1/4, which would be 13/4. But let me just a second. 1 would be 4/4. Yes, that works. I keep writing that integral. If I'd thought ahead, I probably would have said, like, let capital I be the integral I'm thinking of, and then I could just keep writing capital I when I do it. But, you know, I didn't think of that. You know, all of this crap, I'll just not put it in. And now I just have to multiply everything by 4/13 and it should all work out. So 4 over 13 times 1 over 2 would be 2 over... And I'll just stick a big plus C on at the end. Ah, lovely. Well, sort of. It's not that lovely, but I deliberately made it difficult just so you could see where all the numbers went as I did it. So all the 2s and the 3s kept coming out, and it caused this final number to be different. If it had just been an e to the x and a sine x, then all the numbers that came out would have been 1s. And when I did this over here, I would have gotten a 2. Right, there you go. That's the going round in circles concept. So when you do reduction formulas, which are a thing that you can do, that choosing what to integrate and that going round in circles are common strategies that get used when you do reduction formulas. So just to finish that off, we had various strategies. So strategy number 1 was differentiate to get simpler. And that happened when I did that x, and the x differentiated to make a 1, which was much simpler. Strategy number 2 is integrate what you can. So I didn't know how to integrate arctan, so I couldn't make it be the one that had the dash because it would be integrated. Strategy number 3 was try 1 times the thing. And strategy number 4 was go round in circles, which is really just code for keep an eye out for the original integral. If at any point you come back to where you started, then you can do that trick where you put them both on the same side and you end up with the integral disappearing. There you go, that's integration by parts. Yeah. What else were we going to talk about with integral? Trig substitution. Sure. Yeah, I should write the full No, I'm going to abbreviate them both. It's like people saying on television, oh, there's a new app. Hate the word app. I've only just gotten used to app, which is short for application. So anyway. So trig substitution. Okay, so trig substitution on your list of techniques is like number 0, 1, 2, 3, 4. It's about number 5. Okay, it's not the first thing that you try. If you're going to do trig substitution, first you try just do it, then you try rewrite it, then you try ordinary substitution, and you try integration by parts, and then you try trig substitution. Actually, not always true. Trig substitution is designed specifically for things that have stuff in them that looks like it came from Pythagoras' theorem. So it's designed for things with half powers or roots, and where the thing inside the half power or the root is like something squared plus or minus something squared. That's what it's designed for, that shape. So here's some examples. You might have like something like that. That would be, if you saw that somewhere, you might use a trig substitution. Or if you saw this somewhere, something like that, you might use a trig substitution. Or even just a second. Let's put the x first, just to show that that's a possibility. Or even something like that. Doesn't even have to be half powers. It's not really important. The key is that you have powers or roots, and the thing inside them is, made of at least one square. Don't even need both of them to be squared. You just need the x to be squared. That's what it's designed to do. It is not the thing you should do for all of those. Even if you see something of this shape, the first thing you should do is see if you can rewrite it or use substitution. Okay? If you just had x squared on 3 minus 9 squared, I'd just expand it out. All right? I wouldn't try expanding out the thing with the 5, but it's technically possible. If you had something that had an x on the top of this one, I'd use ordinary substitution because the derivative of the thing inside there is nearly there. So you need to check that it's not something else before you launch into trig substitution, because it takes ages. So you want to check if there's another thing first. So note. Check simpler methods first. Okay. Now, I'm sure I remember doing a trig substitution seminar like really recently. It may even have been last semester, and I did lots and lots of examples. So check it out, see if you can find it. But what I did want to say today was what it's used for, so that you can tell when you probably should use a trig substitution. And the second thing you want to know is how to decide which trig substitution to do. Which I've talked about in other videos too. You decide which trig substitutions to do by, well, there are two methods. One is to just remember, and I'm not good at that. Just remember that if you see x squared plus something, you should do some sort of tan thing. And if you see number minus x squared, then you should do sine. And if you do x squared minus number, then you should do sec. Even that I have trouble remembering off the top of my head. I remember it by making trig identities that are the same shape as this thing. So I'm just going to do some examples of just making the choice. So, the important thing to realise, and I probably should have said this first, is that the reason trig substitution works is because you rewrite this in terms of a single thing squared. Trig identities turn things like 1 minus sine squared into cos squared. And then if there's a square root, then you square root the cos squared and you just get cos. It makes square roots go away. That's why it's so useful. So I might just say it works because of trig identities. And just like all the other special methods, it doesn't do your integral for you, it just turns it into another integral that you then have to do. So, and the unfortunate thing about it is that it turns your integral into another integral that involves trig functions that you have to then know how to do. Which is why they spent time teaching about how to integrate things with trig functions before they got to trig substitution. So, how are we going to make the choice? I'm going to make the choice based on the trig identity. Use the trig identities. That's how I'm going to make the choice. So for example, I see an integral with random stuff in it, and somewhere in there I have a 6 minus 2x squared. Okay? There's stuff here. I don't care what the rest of it is. I just want to show you how I make the decision. So I notice this. I've already tried, I'm going to assume that I've already tried to do it by ordinary, thought out how it might turn out if I went for ordinary substitution. And then went, no, that fails because the derivative of this isn't there. And then I'm going to try trig substitution. And because I'm going to do that, I know there's going to be a trig identity somewhere in my working, so I'm going to think of the trig identity first. So I'm going to leave a bit of a space to say what x is. And it's backwards from ordinary substitution. Ordinary substitution, you say u is equal to stuff in terms of x. And in trig substitution, you do it backwards. You say x is equal to something in terms of u. Okay. Or theta, or whatever letter you like. I don't like using theta because I can't draw them without them looking just like zeros. So u is a good thing. So I'm going to come back to that in a second. And somewhere in my working, I'm going to use trig identities. So I'm going to write one down now. The only trig identity I know off the top of my head without having to think hard about it is this one. Cos squared plus sine squared is 1. Now I have used the letter u, and that's important because I wanted to keep track. I'm going to have something in terms of u here. So at the moment, look at this. This is a variable squared and another variable squared equal. So this bit is the wrong shape because the thing I have here is number and variable. So I need to make a trig identity that has a number and a variable. So for example, I might do this. Like that. Cos u squared is 1 minus sine u squared. Now I could just as easily have done sine u squared as 1 minus cos u squared, but as I said earlier, I like things in alphabetical order. And also I know in advance that if I put the sine u in at where it is there, then when I differentiate I won't get annoying minus signs. So this is my good plan, and this is the right shape. Number, variable squared, which is the same shape as this 6 minus 2x squared. So my goal is to make this look as much like that as possible. And the way I'm going to do that is first I'm going to change the number. Just multiplied everything by 6, and now it's very close to what I want. I've got 6 minus something squared, something with a squared in it. I would really like this to be equal to 2x squared. That's what I want. So just let me put that in a box somewhere and I'll figure it out. So I want 6 sine u squared to be equal to 2x squared. So 3 sine u squared is x squared, and so therefore root 3 sine u is x. That's what I want. Yay! All right, that's what I want. So I'm just going to write this backwards, if you don't mind. That was my working. So note that x is root 3 sine u, so therefore x squared is 3 sine u squared, and 2x squared is 6 sine u squared. And so therefore 6 cos u squared is 6 minus 2x squared. Yay. So if this had a square root, then I would go, sweet, let's do the square root of both sides. And I've magically turned the annoying square root into something a lot simpler. This seems like a lot of work, right, just to make that decision. But the reason why it's better than, for me personally, than other things, is because I would have had to write this working down anyway. If I was going to show all my working, I would have had to do all the trig identities and the calculations. And so if I was going to write it down anyway, I might as well use the working that I would have written down anyway to help me figure out what to do. There you go. So if I was going to use a tan or something, this is my integral this time. It's got all this other stuff and a 5 plus 3x squared. I could do exactly the same thing. I can never remember the one that goes with the trig identity that goes with tan, but I always start with the cos and the sine. So at the moment, this is variable squared plus variable squared. This is number plus variable squared. This is the wrong shape. If I rearrange that, I'm just going to get number minus variable squared, which doesn't match. And so I'm going to need to get a trig identity that's got a number plus. If I divide everything by cos, then I'll get this. So I'm dividing by cos u squared. That's what I'm doing. That is so not readable. Sorry. Okay. And now this is the right shape. It's number plus variable squared. This is number plus variable squared as well. I need there to be a 5 there, so I'll just go 5. And it's nearly right. All I need is for this to be 3x squared. That's what I need. So if that's 3x squared is the same as 5 tan u squared. So x squared is 5 on 3 tan u. X squared is root 5 on 3 tan u. That's what I needed it to be. Yay! And so therefore 5 plus 5 sec u squared. The rest of the integral will be a whole other thing. But the making the choice is the bit. Now, most of the time in an exam, it's not going to be root, fabulous square root time stuff. It's not impossible, but They're usually friendlier than that and will arrange for things to be, you know, put instead of a 3, they'll have a 9, so that when you do the square root later, it'll come out to a number that you like. And they'll usually arrange for it to only have one of these numbers, not a 1. So it'll be like 1 plus 9x squared, or it'll be 9 plus x squared. So, but I was trying to make the point that to show you where the numbers went, so that if you did see one where they both have numbers other than 1, then you knew what to do. So let me just think. So that's making the decision at the beginning. The problem with trig substitution is that what happens is you do this. Okay, so the process tends to go like this. You decide / get rid of the bit with the square root. You know, deal with the something squared, deal with that bit. That's the first part. And then you figure out how to sub everything in, like the dx and all of that sort of stuff. The x's and dx. With u's and du. Okay, so then you do that. That's how you do any substitution. And then you have to do the integral that you get, which is a trig integral. And you get like a trig integral, which you then have to do. And then at the end, your final answer will be something involving trig stuff, and somehow you're going to have to sub all the x's back in. Sub in u's. And the hard bits are this bit, often, and this bit. Now when you do ordinary substitution, usually the integral you get after doing the substitution is easier. All right? And it's still true in trig substitution. The integral is easier because it was impossible before and now it's possible. And possible is easier than impossible. But it's not like straight up easy, usually. So I wish I had an example to hand that I could talk through rather than write from scratch. Let me just, give me a second. Just going to look one up. I have a horrifying suspicion that that wasn't recording the document camera. Well, I'll know soon enough, won't I? Okay. Luckily, these are not the only ones I have. Let me just talk through some of these examples. I want the one where I've actually got a trig substitution. Okay, so this one started out with this stuff, and I subbed everything in, and it produced this integral here. The first thing that happened was, so now I've turned it into a new integral. I can ignore everything that came from temporarily and just attempt to integrate 48 sine u squared. But the problem is, I can't just integrate sine squared. I have to use a trig identity to turn it into something that I can integrate. And so what I've done is, because I can only remember a small number of trig identities, I know that there's a sine squared in the trig identity that goes with cos 2u, and I use that to figure out that 2 sine u all squared is 1 minus cos 2u, and so 48 sine u squared must be 24 minus 24 cos 2u, and I replace that, which allowed me to integrate it. Okay, so usually that integral that you do involves a trig identity. But then the problem is, all right, I've got a u and a sine 2u. How am I going to sub the x's back in? Because my original substitution tells me what sine u is, not what sine 2u is. So I have a new problem. I can deal with the u, because x was 4 sine u, so I can rearrange that to figure out what u is. That's good. And my original thing has a sine u, so maybe I could just rewrite the sine 2u using another trig identity, which I've done here. And I know what sine u is, because I just figured that out. And earlier in my working, when I did the substitution, I wrote down what cos u was. So the key to doing a lot of this working is you go and find bits of your working that you can reuse to sub it back in. So in this one that I did here, for example, it tells me what tan u is. I can rearrange that to tell me what tan u is. And this can tell me what sec u is, if I rearrange that. So I can find what tan and sec are. Yes, the computer. I can find what tan and sec are, but and that means that if I see a tan and a sec later on, then I can sub them back in. And if I need a sine, then tan divided by sec is sine, if I think very carefully about it. So if you want to talk to me more about that, then feel free to drop into the drop-in centre and I can talk to you about it. And what I would recommend is check out all of the examples that you can get your hands on for trig substitution, of which there are many on the Maths Learning Centre website. Even if you don't watch the video, you can go through the working and see which bits of the working I use to do other bits of the working. And that's one of the reasons why trig substitution is so confusing, because the stuff that you do, you know, I've got 4 steps here, but each of those steps either involves a difficult decision or complicated thinking. So it is not wrong to feel confused or to feel like it's difficult. But what is wrong is deciding that it's a lost cause. Because you can do it. I find when I do these things, this process is in my head. So at the very least, even though I know each of the steps is difficult, I know what I have to do. And it's the sort of thing where even if you ran out of time in your exam, you could just tell the person reading it what you were planning to do later and maybe get an extra mark. Even if you didn't do it, you could tell them what you were planning to do. And that mark could make all the difference between passing and failing or a credit and a distinction. Especially if it was the only mark you needed, right? Exam markers are well known for, if you are 1 mark off of the next grade bound, to go looking to find an extra mark for you. So give them reasons to give you extra marks. Don't give up. At least say, this is what I plan to do. That's my big advice. But of course, you're all going to be awesome at this by the time you get to your exam, because you're going to go and look at the examples and talk to people about it. That's trig substitution. Right. I'm loath to do a whole another trig substitution example because, you know, as much as you can do trig substitution, I'm sure there's a limit to the percentage of your life you want to spend doing it. And I've spent a lot of my life doing it. So I'm going to move on to something else. Okay. It's like exposure to radiation, right? It's cumulative over time. You know, when you go and get an X-ray, the radiographer stands behind that screen. So, yeah. Maybe I need one for the Maths Learning Centre. And say, oh, sorry, that's trig substitution radiation. I can only take so much in my life. Okay, sweet. What could I talk about for the next 40 minutes? On the list on the wall there, I have subspaces and logs and exponentials stuff. I'm still not entirely sure what I'm supposed to talk about for the logs and exponential stuff. So what I might do is, they may be under those headings, but perhaps some people have some specific, maybe past exam questions or other stuff, specific questions that you might want me to go through. You can't just tell me which exam and what question. I don't have access to them. You're going to have to bring me the question if you want it. So, yeah.
Subspaces, I'm still a little bit confused about the idea behind them.
The idea behind them?
Yeah, sort of. I don't know if there's a really specific question I could ask Clay.
That's okay. Idea behind them is something I can work with.
Okay, cool.
Okay. Subspaces, the idea. That's what we're going to talk about. Yeah. Okay, so there are other revision seminars about some of the details of the things that you want to do to subspaces, like find a basis for them or prove that something is a subspace, those sorts of things. Right now, I'll see how I go, but I'm going to talk about the idea. So, the idea goes that vectors can represent multiple things. Now that's the first thing. So, there are three things that vectors are. The first thing is that vectors can represent the coordinates of points. And we're talking to mathematicians here. They have their own meaning of vector. So vector, we're thinking list of coordinates, and it could represent a point. Okay? So you could have 1, 3, which is perfectly good. Vector would be, you know, that point just there. Okay? And, you know, 1, 3, 7 in 3D would be some point in 3D lining up against 3 axes, and 1, 3, 7, 4 in 4 dimensions would be, you know, a point lining up against 4 axes, which I can't directly imagine because I'm not that shape of a being, but it's the same idea. Okay, so you locate things based on their coordinates. Now those points don't necessarily have to represent physical points in space. They could just represent 4 bits of information about a situation. Okay. So technically that's another thing that they could represent. I'm going to stick that in, you know. See if I can think of it. For example, a rectangle drawn on the page could have any number of bits of information about it. It might be 5 centimetres one direction, 2 centimetres the other, 30 degrees rotated, and be centred on the point 1, 3. So I could create a vector that's like 5, 2, 30, 1. 5 bits of information about that rectangle could be represented as a vector with 5 numbers in it. Right, that's the basic idea. If you have a robot arm with multiple different moving pieces, then you can represent the position of each piece with multiple numbers and get like a 17 coordinate vector. And in statistics, you might measure a group of 10 people and write down all their measurements. That's a vector with 10 coordinates. So just because we're used to thinking of them geometrically as points doesn't mean they can't be something else. Okay, these sort of go together, these two. All right, so technically the coordinates of the point is information about that point. All right, the other thing that a vector can represent is a journey. You know, it could be, you know, an arrow, like in physics. You know, it's 5 newtons long and it's in this direction, or a displacement. I'm going to talk about them as journeys rather than as forces. So it could be a journey between 2 places. Okay, so I could have the point, say, 1, 5, and the point 6, 18, and then the journey itself there is the vector 5, 13. Okay, so you'll note that I have drawn all of these as just things with 2 coordinates, and I haven't used my brackets to distinguish between when I mean a point and when I mean an arrow. That's mathematicians for you. Because a set of coordinates just standing by itself without a drawing to go with it could be at any moment a point or an arrow, depending on what I want to do with it. All right. And the final thing that a vector could be is a thing that you can do linear combinations on. You know, I've got A times this thing plus B times some other thing. Linear combination. So if I've got any things at all, whether they are represented with coordinates or not, and I find that when I look at all of them, I'm able to do A times thing plus B times other thing and combine them together to create a new thing. Anything that does that, I can call vectors if I want. So things with coordinates, I can do that. I can multiply them by numbers and add them together, and that's great. Arrows, I can do that too. I can do it to sequences in this course Maths for IT. I can do it to functions, so they could be vectors if I want as well. And so anything that I can do that to, when I look at them as a collection, I can see them as vectors, and that's when I call it a vector space. I'm almost up to the idea. So these are the different ideas. And other than this one, I'm not going to get into that one, but the geometry of points and the geometry of arrows and the thing that can do linear combinations, they are the ideas that make subspaces. Subspaces are made of. So, mathematicians are very interested in things like vector spaces. You know, they're very interested in the real numbers. They're also interested, you know, things that sort of collect together in groups, they're interested in those. So the rational numbers and the real numbers and vector spaces and subspaces. So they're interested in things that collect together like that. And you learned way back in week 1 of Maths 1A things like the rational numbers are closed. You can do any 2 rational numbers and you can multiply them or add them or subtract them or divide them, and you'll just make another rational number. You'll never be able to make anything like pi out of the rational numbers because the rational numbers are sort of self-contained. And so the rational numbers are like a subfield of numbers. They're inside all the real numbers, but there's sort of less of them, and they're self-contained. That idea of self-containment is what a subspace is about. So we have a vector space like all of the possible things with n coordinates, which is what Rn is. And then we might have a smaller part that's self-contained. That's a subspace. And when I say self-contained, it's self-contained based on the things that you know vectors do. Vectors do linear combinations, so I want my subspace to be self-contained when I do linear combinations. Now, this is not the definition, it's just the idea. So if I do linear combinations on anything inside the subspace, I just stay inside the subspace. I can't get out by doing linear combinations. It's completely self-contained. I could imagine taking my subspace, whatever shape it is, and cutting it out of Rn and putting it over here and going, yeah, don't need the rest of Rn. I could live happily here and never break any of my maths, because all my linear combinations work perfectly well inside here without the rest of R3. That's the idea of a subspace. And that is why we're so interested in that whole this thing. So you need it to be self-contained. So no matter what you have inside the thing that you're going to hope is a subspace, I need any linear combination of these things to be in the subspace too. It's self-contained. But that's often really hard to prove, and doing linear combinations is just joining together of adding and multiplying by scalars. So I can separate them out into two separate rules to say, well, you know, or we need AU to be in W and U plus V to be in W. As long as all the additions are self-contained and all the scalar multiplications are self-contained, then all the linear combinations will happen too. Right. And we don't have to worry about all the other things that I care about for vector spaces, like being able to do the distributive law and expand brackets and that sort of thing, because it just works anyway. Okay. There is one other rule for being a subspace, is you need the zero vector to be in there, but you just need there to be a vector in there. Like you don't want to have to say, oh, well, I haven't got any vectors at all. That's a subspace. Sure. So we don't do that. We say we have to have a vector in there at all, because otherwise what am I going to do my operations on? Okay, and the zero vector is going to have to be in there. If there's any vectors in there at all, when I multiply by 0, you're going to have the 0 vector. So we might as well just check that one. So we also need a vector at all, and why not 0? And so that's where our rules come from. Okay, that self-containment implies those three rules. If you, rule number 0, damn it, yes, that the 0 vector is in it. Rule number 1, that if U is in it, then any multiple of U is in it. And rule number 2, if U and V are both in it, then U plus V is in it. That's where those rules come from. It guarantees a self-containment. I call them rule number 0, rule number 1, and rule number 2 because rule number 0 has a 0 vector. Rule number 1 involves 1 vector, and rule number 2 involves 2 vectors. Gives me a certain glow of satisfaction that I can do that sort of thing. Okay, that's why I care about those rules. It's that self-containment, saying, hey, this works like a vector space in its own right. Okay? There's a whole other idea, right? There's a whole other idea. So this idea belongs to this mathematical concept of being able to do mathematical operations. Okay? I can do these addition and multiplication sorts of things. That's what this idea belongs to. But there's another idea about subspaces that belongs to coordinates. Belongs to things with coordinates of points and journeys. Okay? So that idea is what creates the shapes that we imagine when we make subspaces. So this is like the maths operation idea. And then we have the geometry idea. It's still a self-contained sort of thing. But now we're going to imagine our combining of vectors together as a geometry thing. So I know that if I have some vector plus another vector, then I could imagine that vector and that vector as points or arrows. There's my point U and there's my point V. I could imagine them as points if I want. And that would be a particular location that the U and the V mean. But then U plus V, I could only find it by turning these into arrows. So I could go, that's the arrow V. And I could go, the vector U plus the arrow V produces the answer U plus V, if I wanted. Or I could just as easily go, the point V plus the arrow U produces the vector U plus V. Or if I was being particularly fancy-minded, I could say that the parallelogram created by both vectors, the opposite corner of it, is where U plus V is. Which is how Newton first imagined forces adding, by doing parallelograms. So I have this geometry idea that I can, if I want to add vectors, I have to think of the second one as a journey. So I have a place, which is U, and I add the journey V, and I result in a new place, which is U plus V. Okay? So there's two ideas there. One is that if you want to point to B in a particular set or a subspace, you think of it as a point. If you want to think about how to add them, you need to think of them as arrows. So being somewhere, U is a point. Adding, U is an arrow. And that's just mathematicians for you. You just have to get used to it. Just like you're allowed to represent half as 0.5 or you represent half as one out of two things, or comparison where there's 2 times as many of these things as there are of these things. They're two different ideas about what a fraction is, and I can use the same number to represent both. This U can represent 2 things. So because of that geometry idea, I can start thinking about what it means to do addition and scalar multiplication. So suppose I had a set which contained a point So if I've got the point U, and I'm allowed to have that point, and if I have to have all the multiples of U as well, as per rule number 1, then if I'm going to have U, then I also have to have 2U. And I also have to have a half of U. And I also have to have 0U. And I also have to have minus U. And I got to those points by thinking of different arrows. There's U. And there's an arrow that's half as long, and that's half of U. And there's an arrow that's twice as long, and that's 2U. And they created all these different places, and together those places create a line. So if I take a single point, and I do all the multiples of that point, and I have to think of them as arrows to do multiples, I create a line. That's spanning for one thing, one point. And if I add things together, okay, wait a second. if I pick 2 points on this line and I add them together as arrows, I'll just go up a bit and then back a bit maybe, or up a bit and then further up. I can't escape this line by doing addition and multiplication. And so this line I know is a subspace because it can't be escaped from either. And so now I have this picture that, ooh, lines are subspaces. So subspaces aren't just random things that happen to be closed. Ooh, lines is an example of that. And they could also be planes if I do the addition. So what if I had this one and that one? I could add them together, which would be here. I could go u plus 2v, which would be here, u minus v, which would be here, and I could create this grid of all of the things, damn it, not parallel. I'd be able to make all of these things if I was allowed to do any amount of adding and subtracting that I wanted. All of them. So if I had 2 points, I could create from them this grid of other points. But then if I was allowed to do scalar multiplication as well, I could shorten everything and I would fill in all the gaps in between. So, because I'm allowed to use anything here and anything here, I can get anywhere I want. So the addition sort of fills in the gaps between things, and the multiplication sort of fills in the spaces on the outside and the inside. Yep?
Oh, so the top plate would be a subspace, right? Only if it's in R3.
Right, yes. So you're saying this in a plane here, that's not a subspace if I do everything? Is that what you're saying?
Yeah, but it would be a subspace if it's 3 dimensions.
Yep. So here's where mathematicians like to change their technical language so they don't have to keep making that sort of thing. So you're right, in R3, if I got 2 points, I could create from that a plane by adding them together. And I wouldn't be able to escape that plane, and that plane, maybe the surface of this, for example, would be a plane, and that would be a subspace. And down here in R2, technically, if I do addition and scalar multiplication, I can create the entire of R2 from those 2 points. And you're going, oh, but it's not smaller than R2, so it's not a subspace? Well, mathematicians go, do you know what? It doesn't have to be smaller. I'm still going to call it a subspace even if it covers everything, just because then I don't have to say it's not a subspace. Then I can just say linear combinations of anything is always a subspace, and then I don't have to worry about it anymore. There you go. It's just like mathematicians saying that a square is a rectangle. Because then when they say, well, the rectangle with the minimum perimeter for this area is this rectangle, oh, but it's a square. That's okay, squares are rectangles too. So that's why mathematicians like to do that sort of thing. They have nice inclusive definitions so they don't have to keep going, oh, except when it's a square, oh, except when it's everything. Okay. So I now have some pictures of what subspaces look like. They tend to look like planes and lines and whatever, or bigger versions of those. And I have some other ideas here. I know that a subspace can't have a hole in it. Can't have a gap between 2 points in a subspace because the scalar multiplication would fill in the gap. And it has to go on forever, because if it didn't go on forever, I wouldn't be able to multiply my vectors by 50,000. And I'm supposed to be able to use whatever number I want. And it's got to exist on both sides of the origin, because if it only exists on this side, I wouldn't be able to multiply by -1 because I wouldn't be able to produce the other side. So subspaces can't have gaps. So if I imagine what something looks like, I can go, oh, it's got a hole in it, it's not a subspace. Now, it's not a good enough answer for your exam, but it's a good enough answer for your head. If all you had to do is true or false, is this a subspace? You can go, no, it's got a hole in it, it's not a subspace. Okay. Beautiful. So we now find that when we have the geometry idea, we make lines, planes, 3D things. You can also just make a single point. That will do it too. It has to be the origin. Because if you have a single point that's not the origin, you blow it out into a line when you create a subspace from it. Okay, so we have two ideas now. We have this concept of being closed under scalar multiplication and addition, which is important to us because we like things to be self-contained. And then we have this geometry idea that we have these planes and lines and stuff through the origin. So now we have some shapes in our head. And then the third way of looking at subspaces, there's actually two more, is that, well, just a second, if coordinates represent pieces of information about something, then it may be that those bits of information are related to each other. Okay, so how far this rectangle is rotated will change where its centre is. And so the rotation and the centres there will be related to each other. It's not like every possible combination of numbers is going to be able to represent a rectangle. And so I'm going to have to, need to figure out which combinations of numbers really do represent rectangles, and only some of them I care about. So the way I do that is create equations. And say only if these coordinates satisfy this particular equation do they represent the thing I care about. And so I'm suddenly now into this idea of creating things out of equations. So I can make sets I can go, a set of vectors such that equations. And what that means is I'm only allowed to use the vectors in my set that satisfy these certain equations, and all the other ones I don't care about. And what I'd really like to hope is that I really don't have to care about them, because the vectors that do satisfy the equations are self-contained. And I don't have to care about all the ones that don't satisfy the equations. And so I would really, really like it if my equations made a subspace, because that's self-contained. Okay? But in general, all I need to do to figure out what shape this is to go through every point and check whether it satisfies the equation and colour it in if it does. All I have to do. And some equations, from experience, we know what they look like. If I had x squared plus y squared equals 1, that'd be a circle, and the circle's got a gap in the middle, so it's not a subspace. And if it was x plus y equals 2, and I was in R2, that would be a line, and I know that doesn't go through the origin, and so it's not a subspace either. And it turns out that as long as these equations are linear equations, and they have no constant term, so they're homogeneous, then it definitely means you have a subspace. So I now have a way of saying, hey, I've got these equations that represents the things I care about. I don't even have to draw them to tell whether it's a subspace. I just have to look at what kind of equations I have. If they're linear equations that are homogeneous, definitely subspace. I can be sure. Which is kind of cool. So now we have the idea of being self-contained, and we have the idea of creating lines and planes, and we have the idea of equations. And there's one more idea, which is the same as this geometry idea here, which is, well, what if I'm thinking of it exactly like I'm thinking it here, and starting with a couple of points and seeing what I could create from them? That's what span is. So the span idea is, I do span of some vectors. And this is creating all the linear combinations. And well, duh, of course it's a subspace, because I've done all the linear combinations. So if I'm just going to do linear combinations of linear combinations, they're still linear combinations, so I'm never going to escape. So it's subspace. Now you'll notice that our way of understanding subspaces was to figure out what happened to all those linear combinations. So in a way, span is like the fundamental idea of what a subspace really is. And so what I would really like to do is I would like to rewrite all subspaces as spans, because then I know how to make them, rather than just how to talk about them, which is what the equations do. So that's my hope. rewrite as a span, and that's what a basis is for. There you go. That's my ideas of subspaces. The reason why it can be so complicated or difficult to think through is that you're thinking about objects in multiple ways simultaneously. How do I specify a collection of points in space? Well, I could tell how to make them by spanning, or I could have an equation they have to satisfy, and I need to be able to turn one into the other. You haven't been taught how to take a span and turn it into an equation, but it is possible. But it's much more important to be able to take an equation and turn it into a span, because it's better to know how to make things than just how to check if they're there. Yep. And why do we care? A, because so cool. Like that any linear equation has to be a subspace, and anything that is a subspace has a linear equation. I think that the connection between equation and span is really kind of very interesting. But it is not for nothing that I did a PhD in geometry, okay, because I'm interested in these things already. And the other thing is that, you know how I said right at the beginning that more things, that anything that can do linear combinations properly, you can call a vector space? Well, that means that if I find some things that do linear combinations, then I can call it a vector space, and I can use everything I know about how vector spaces and subspaces work to tell me how those things work. So functions, I can add them to make new functions, and I can multiply them by scalars to make new functions. And so I could think of functions as vectors if I wanted to. And derivatives, it turns out, act on functions the same way that matrices act on vectors. And so I can use my understanding of how matrices work on vectors to understand how derivatives work on functions, and therefore solve differential equations using vector ideas. So all that thing about homogeneous solution and then you add the particular solution, that thing, well, you can apply that to solving equations involving derivatives, to finding functions. You can apply that to finding sequences of numbers and counting things. Anytime you have things that behave like vectors, you can apply the same thinking to them. And that's why they teach you about subspaces, in the hope that you'll notice that shape of thinking and being able to copy it to a new situation. Doesn't always work because it's hard to notice those situations. But it's still a thing. So if you do Maths 1B, in the first couple of weeks, you're going to use some of the ideas from subspaces, in particular the ideas from matrices, to make a basis of functions and use that to create your answers that you need. They won't call it that, but that's what you're doing. So the concept, yeah, that's why it's so important, because it applies to lots of things. That's why it's so important to learn about rates and ratios when you're in year 7, because that idea of two things being in proportional relationship is such a big idea that's useful all the way everywhere in science and maths. So that's why they teach it to you. Same deal here. This idea is useful. Plus, you get to learn a bit about proofs, which helps you understand how mathematicians behave. Mathematicians like proofs, and it's good to see them doing them so that you can get a feel for when you next have to meet a mathematician, how you can talk to them. And everybody, whether you're a mathematician or an engineer or a scientist, has to work with a mathematician or at least read things that mathematicians wrote at least once in your future. And so it's good to know how they behave, and subspaces is a good place to learn that. There you go, I've waxed lyrical about why you've learned them. Whatever. All that does is make you feel better about it, but you've still got some exams to deal with. So I'd recommend going and having a look at some of the other seminars to see how those ideas play out when you try and solve systems. So yesterday we talked about finding bases. Was that only yesterday? Oh, man, SWOT week has got so much in it. So, yeah, there you go. I hope that helped, and I'm going to stop.